I really appreciate you showing up so early on a Saturday morning to hear me talk about CMake. I'll do my best not to put you right back to sleep. So I'm not going to ask who of you is a C++ developer, because otherwise you wouldn't be at this conference. But I would like to ask who of you would consider themselves a C++ library developer? Okay, a few hands. So why do you think this talk is targeted specifically at C++ library developers? Any?
It says so.
It says so. Yes, for sure it does. No, so it's not because what we're going to go through, what we're going to learn today is not applicable if you're a C++ application developer. I think your code will probably benefit greatly from it. But the reason there's a different one. And think about it maybe this way. So if you're an application developer and I want to go ahead and use your application, I can go to the GitHub pages and download the latest release. I might brew install, apt-get install, snap install your application and go ahead and start using it. However, on the other hand, if you're a library developer and I want to use a library, then they're a bit different. If I'm on Mac, okay, maybe I can still brew install your library. If I'm on Ubuntu and I don't need the latest version of what you have, you have packaged it, I can sudo apt-get install protobuf, sudo apt-get install boost. Fine. Maybe I can also use a C++ package manager, like Cone or VC package, to pull in that dependency. But that's not me. My name is Kerstin Keller, and I've been a software developer at Continental for almost 12 years now. And currently, I'm working on the open source library CMake, open source library ecal. So I know very well the library author perspective. But also during my time at Continental, I've been working on integrating open source libraries to make them available for our other developers. So that means I need to build them for the platforms that we want to use, with the compilers that we have to use, with the flags that we need to use. And all of a sudden, I need to interact with your build files. I have to build this library, and this is the main difference. So if you now, as a library developer, you've done a good job, it's a really easy task for me to integrate that library. I have to figure out, what are the licenses, I need to build this, and then see how to consume it, and I can be done. However, if you have not written clean CMake code, I can get into big trouble and feel like that person. Because during my work for integrating libraries, I've integrated over 100 open source libraries for our internal usage, and I've seen things there that shouldn't probably be done, and things that should totally not be done. Like there's one library forcing the MSVC static runtime onto everyone, and then of course nothing builds anymore, nothing links anymore. So I guess if you're a library developer, you want your users to have a good user experience, and that includes having a good build experience. So with this talk, we're going to go through the 5 points that will make it really easy if you follow these 5 points, it will make it really easy for other users to go ahead and use your library, and thus have a good build experience. And in the end, it will also hopefully make my life as integrator of libraries easier in the long term. So we're going to be reading CMake Code also. So if you've never read CMake Code, it might be a bit challenging to keep up, but I think if you have basic CMake knowledge, you should be fine. Okay. So let's start with the first point. of how to write good CMake files. Use CMake. And I guess it should be kind of obvious, but let me tell you the story. So I was giving more or less the exact same talk at our local C++ user group in Frankfurt half a year ago. And a few weeks later, I meet one of my former colleagues who's all about clean code. He initiated some clean code trainings within our company. So I'm really excited to talk to him about clean CMake. But he interrupts me. He's like, Kerstin, CMake? Are you serious? At my new company, we're using Bazel now. It solves all of our problems. And then, basically, I just have to think about this XKCD comic. So, situation, there's 14 competing standards. 14 what? We have to find something new that solves all the problems, and then there's 15 competing standards. So don't get me wrong, I'm all about new tools, new technology, but the situation with the build systems in C++ is it's a bit special, and we're going to talk about why it's a bit special. So the statement which I want to make is, if today, at the end of 2024, you're maintaining a library and you want your users to have a good build experience, you should be using CMake. And let me show you some numbers for this. So these are numbers taken from the Meeting C++ Developer Survey conducted by Jens on the Meeting CPP website. And on his website, he asks questions like, which C++ standards do you use in your project? Which C++ 14, 17 language features are you using? Which IDE do you use for C++? Which classic design pattern is your favorite? But he also asks, what build systems do you use? And when you go to the website, you can choose, I think there's like 14, 15 different build systems, but I just included the ones here scoring more than 10%. So, first one, GNU-make. We're C++ developers. I guess anyone has at least read at some point a make file. How many % do you think are using make as a build system? So there's like about 4,000 people answering this survey. 20%? 20%, let's see. So for make, 34% of people are saying they're using make, and GNU-make, I didn't even know that was a difference. Still 15% of people. So, okay, quite high. The next one, MS Build. You're on Windows. Like if you're on Windows, there's really no way around Visual Studio. So what do you think? Like, where are we here? 70 for MS Build? Maybe that's a bit high. So almost like 24% of people say. Next one, Ninja. So I think it's the default build system if you're using CLine. It's newer than Make. Also for Visual Studio Open Folder. CMake support is also using Ninja as build system. So any guesses? 10? Actually, it's also 25. So, but now interesting one, CMake. Where do you think we're at? 75. You nailed it, really. Good job. So, I don't know, like, I don't have personally met anyone who's like directly using Ninja, so maybe like these numbers are also a bit higher because you're using Ninja in combination with CMake, could be. Which I was really interested that it's on the list with more than 10% is CMake. Like, okay, Qt Creator, if you're using it, that was the default build system that came with it. So it comes in at actually 12%. Email, Bazel, which might solve all of our problems. I don't know. It's 4.6. So maybe if I would be giving this talk in a couple of years, we might have a different answer. But I want to emphasize today, end of 2024, you want to have your users have a good user experience, go ahead, use CMake for your library. Okay. So point number 2 of the 5 points, how to write good CMake. We need to understand how CMake works internally. And the thing is, think about Git. When you started using Git, probably you knew, okay, I need to git pull, I need to git commit, I need to git push. Without really understanding how Git works internally, there's like a tree behind this, there's the stage and the index and so on and so forth. And that kind of works fine until it doesn't anymore, because something unexpected is happening, which if you don't understand how it's working internally, you're unable to solve. And it's the same with CMake. So to understand how we write clean CMake files, we really need to understand how CMake works internally. And to do that, we want to take a look at a very, very simple project, one library, one executable, and see how we can build that. So this is the source directory of our example library. We have a library called foo. It's in a foo subdirectory with a foo CPP file and a header file. Okay, let's see. So the foo header file is inside include foo.h, namespace foo, and we have a function returning an integer. Nothing special here. And we have the corresponding implementation, and we include foo/foo.a. And what else could a sensible function returning an integer return except 42? And then we have a usage example, main CPP. We also need to include the header file, and we just print what the function is doing. So the question is now, how do we build the setup? And to understand like what CMake is doing, we kind of want to first understand on a low level, what does the compiler do? Because basically, in the end, we need to invoke the compiler, and we will need to figure out which arguments we need to pass to the compiler, because after all, building it will just be a bunch of GCC or Clang or MSVC calls in the end. So to build our executable, what do we need to do? We have to build create a shared library from foo CPP, and we need to pass the include paths, and we need to pass FB shared so we can get a shared object. And then we also need to invoke again GCC or G++ and compile the main file. And this time we also need to pass the include paths from our library, and additionally we have to provide linker directories and actually linker commands to link the library. Basically, when we compile something, it all boils down to this. It doesn't boil down to these exact commands, because the compiler would first generate object files and later link and so on and so forth. But it doesn't really matter. Build systems, they will generate a bunch of command line calls for the compiler. And for GCC, there's tons of options which you can pass. The man page, it has 26,000 lines. The Clang man page, not so well documented, only 3,500 lines. So there, you get it. There's like a lot of options. These options which you can pass to the compilers, they're also grouped by functionality, like options for diagnostics, options for optimization, preprocessor, machine-dependent objects. So there's a whole bunch of them. So when CMake started, they were kind of doing like just a light abstraction on make files, which you would be prior writing. And they would follow what I would call like a global variable approach. So you would just like globally do things like include directories, link libraries, link directories, like things you would also write in the make files. And the problem with this is that this is not sustainable, because it gets complicated quickly, and CMake internally needs to have another model. But yeah, let's quickly take a look here. So yeah, add library. This is what kind of we would have to pass, and we can add just globally set the flags which we want to compile, and also globally set the include directories. But this is not what we want to do. Don't look at it too closely, because we do not want to write CMake like this. What we want to do, on the other hand, is we want to write modern CMake. And modern CMake kind of means to use a target-centric approach. And what that means, I will explain in a second. So, then we ask you, who of you starts a new CMake project from scratch? Okay, this is good. And who uses a template like CMake init or something like that? Okay. Or maybe copy from some other old project that they have. Yeah, some, okay. So in order to build a simple project, what do you think, how many lines of CMake code would we need in total? Just think about it and we will get back to it. Okay. So now, when we want to write CMake files for it, what we would do is usually use a folder structure like this. So we would have a main CMake file on the main directory, and then we would have additional CMake files in each of the subdirectories of the targets that we want to build. And let's just quickly look at what those would contain. So the main CMake file, it always needs to contain a CMake minimum required version, because this is for what how CMake internally initializes its not variables, but the options and the policies. So they they try really hard not to break your build with newer versions, but they also want to add new features. So with saying CMake minimum required, you say which way you kind of like, in which baseline you want to start. And you always need a project call. This will initialize some CMake variables. If you're building a Visual Studio, using the Visual Studio generator, it will generate your solution file. And you will just include the subdirectories for the library and for the executable. This is how we would build the library. We would say we want to add a library, and we want to target some sources on top of this library. We have a file set, the header files, and I will explain this in just a little bit, and also we need to compile for CPP. And then, on the other hand, for the executable, we add an executable, we create a new target, we add sources, main CPP, to this executable, and then we also link the library. We target link the library. So if you followed, those were 28 lines of code, but with formatting. So if we put everything flat, we could do it theoretically in 7 lines of code. So it's not so bad. But since you're all starting CMake files from scratch, then it's good anyways. Okay. So now let's take a look at how what is CMake now doing internally if you're declaring these targets and building this. So basically all entities that you want to build, that they are targets. So an executable is a target, a library, a test, and they depend on each other. And this lets CMake figure out also a build order. And there's properties on targets. And these properties control everything about the build process and the target itself. So they control the file name, the file type, the extension, the output directory where it will be built. It contains build instructions like compiler and linker flag, install instructions, and also IDE association. So on each target, there's 396 different properties as per CMake 3.31. And most of these properties are private to the target. But there's also properties which are interface properties, and they will propagate to anyone who links to that target. And there's 19 of those interface properties. So now we want to take a look at 6 properties of the target and see how they are initialized or how they are set by the different commands which we have in our CMake file. Okay, so a library, we create the library. And then we will take a look at these 6 properties. It's the sources, the interface sources, include directories and interface include directories, link libraries, and interface link libraries. So, target source, adding something to the target. We have the file include foo/foo.h. So because we say this is public, it will populate both the private, the sources variable, as well as the interface sources variable. The base directories of this file set will both affect the include directories target property, as well as the interface include directories property. And then lastly, we privately add main CPP to this target, so it will also be added to the sources, but just the sources. So now the same for the executable which we're building. At executable, we will look at the same 6 properties. So at executable, we have it. Next, we will target the sources. Okay, we'll populate the sources. And now it gets interesting, target link libraries. So this will now do a couple of things. So this will now first add to the link libraries and we're building on Windows, we'll put here the lib file that the output produces. But it will do more. So it will take in these properties, take a look at the interface sources. So now there's the include file, and it will add that to now the sources of the usage. And the same for the interface include directories. It's, there and will be added to the include directories there. And this is all because we say we want to privately link the library. If we wanted to publicly link the library, the transition properties would be a bit different. Okay. So this was point 2. We understood somehow, maybe if it's the first time you've seen that, might be difficult, but we understand basically how CMake works internally. Okay. So package our library with CMake. So basically, we can only use a library if the library has been installed by the user to a custom location. Maybe a dependency manager can trigger this process. And I want to take a look in CMake what needs to be done to actually install the library, because also it's not so complicated. So in C++, since we don't really have a thing as a C++ package, we saw that earlier, we pass include directories, we pass linker flags to the compiler. So what now when we package something is that we need to collect the compiled libraries and the header files, but also we need to provide additional information really on how someone else would consume that library. So where is the header files? Where and how is the library shared object files called? And do we need to pass additional defines or something else when we're using that library? So this is additional information which we have to collect and which we need to make available somehow. And it would also be nice if the package that we create would be relocatable, so we can put it in user lib, we can put it, or the package manager can say where it should be located. So that's always a good property. So for this, we will take a look at the source tree. We will take a look at the CMake commands that we write in our CMake files, and then we will see how that influences the install tree. This is the file we had, add library, and target the sources. So additionally now, we said we want to package the header files and the library itself. So we call an install command with targets foo, so the target we have. And we will also export that. I will talk about this later. And we also install the file set. So this has made things like installing the headers a lot easier. And by just using this command, we make sure that when we install this, we package the header file and we package the library itself. And the next thing is we need now this usage information for the consumer to use our package. And this we install the targets which we have previously exported. And this will cause CMake to generate 2 more files, like a foo targets.cmake and foo targets config.version. So you can have multi-configuration packages where you package, debug, and release artifacts together. And then, last but not least, you need a file that tells CMake, I have a library. And this is the foo config file. Okay, so after all, this is the package that we have. You can take it. And quickly, we take a look at these files which CMake has generated. So we have foo config, and this will just make sure to include these target files which have been automatically generated by CMake. And this is the file that when you have a FAM package call in your CMake to locate a different dependency, CMake will go ahead and have a bunch of search paths where it's going to go through and look for these config files. Often it's just like an include of the targets, but you can also set additional information about the library, like what subcomponents did you build from the library. And what you can also do is you can also generate a foo config version file, but that's not mandatory, and then you can do things like find a specific version of your library. So now this is what CMake generates, a foo target file. And after all, this file does not look too different from the file which we originally wrote. There's also an add library call. Now it's called foo::foo. We export it into a namespace. And we have these file sets to add to the library, which we also did manually. And then in the configuration specific file, there's also the location. Where is the library located? Here. Yeah, and with this, we have a relocatable package, and you can provide it to CMake, so it can be picked up by the find package call if you install it to default location, so like user local, or if you're providing a de-CMake prefix path variable to CMake, so CMake will look in those ones too. Yeah. So we saw just earlier, we don't have any more the foo target, but we have a foo::foo target. It's different now. And to mitigate this, to treat our target differently, what we recommend is usually to add also an alias target when you create your library. And that means now that you can, within your build tree or from externally, you can reference your library in the same way. So this means we also have to make changes to our foo usage example. So we need to change foo::foo. And now, if we just add another find package call, then this is our usage example, and you can give that to a user who wants to consume your library to see how to actually use it. Okay. So it's not that hard to properly install, if you know how to do it, to properly install your library. And in the next chapter, we will see how to handle the dependencies or other outside dependencies correctly. Okay. So let's summarize real quick what we learned in this find. So we use CMake to package our library. We ideally document how to build the library and also document in code, preferably, how to consume and use that library. And by following these steps, we can ensure that a user can easily consume and integrate our library. Okay, so the next point, we saw how to install something, but I also want to talk about how do we consume something now, because there's also things which you might be doing not ideally. Okay. So in C++, the standard library provides a set of libraries. There's the STL, algorithm, chrono, since C++11 threads, standard format. But if you compare it to other programming languages, it's rather a smaller set. For example, Python has like a lot more extensive, I call it standard library. So traditionally, if you want to pull in other libraries, they would mark it. This library, it has no external dependencies as a point of quality. Or this library is header only. So why? Yeah, because there's neither a standard build system nor package format. So it used to be that integration of other libraries is really hard. But with CMake, we now have an extraction to locate another library. If this library was also built with CMake, and this is why it's so important if you're writing a library to stick to CMake, because if everyone is using CMake, then you can get really good integrated builds, but if some other packages are not, then it gets messy. So yeah, with CMake, we have an extraction now to locate another library, and that abstraction is called find package. We saw it. And let's talk about a few things now when you're a library author, which I would not recommend you to do. So the first thing which I would not recommend you to do is to vendor your libraries. But this holds only true for libraries. If you're an application developer, totally different story. It's your job, really, to make sure all the right dependencies get pulled in. So vendor kind of means you include another library as part of your build. So on the left side, we can see if we're not vendoring a dependency. We're calling find package. Maybe we need CMake now, we need gtest now to test foo, and we also have a protobuf requirement. So we have these find package calls. So what you tend to see also in other libraries is that authors pull in these dependencies and add them as part of their build. So one way how you could do that is you could add a submodule to your project and then just add that submodule as a subdirectory. The other thing is you could download the source code for your dependency from the internet using fetch content declare and fetch content make available. And I really get the advantages of this approach. It just works. So anyone can go ahead and kind of build your library. The disadvantage is it doesn't scale because now you have tied your package to a specific version of a dependency. And now you use gtest, but I, as an application, I pull in multiple libraries. They also use gtest. They use gtest in a different version, and then, yeah, you get version conflicts. So this is something really that a package manager like Chrome can easily solve in the end, or maybe not easily, but can solve can solve in the end. So the point is, while this might seem like a good idea, I recommend against it, or at least make it optional. So what are alternatives? So the alternative is really to provide it from the outside. And you can do that in CMake with using a relatively new feature, dependency providers. It was made available with CMake 3.24. So you pass from the outside how you find your libraries. And there you can still download it or whatever. But then when the user wants to use your library, they don't see that and they don't have to do that. If you're on older version than CMake 3.24, but there's really not a reason to not be like on a really new CMake version. You can work around that using find dependency CMake files, but I'm not going to go into this. Okay. So the next point when you handle dependencies, which I think is kind of important, is handle dependencies the modern way, and this is the target approach way. Let's take a look at the left side, modern CMake dependency usage. So we find a package and we target link the library that has been exported from that package. But however, you might often still see stuff like this. And this really comes from a time when libraries themselves wouldn't be exported with CMake. They wouldn't be built with CMake. So what CMake did is they offered alongside CMake these find modules. So they have written files that will locate on your disk where is a specific library, where are the corresponding header files, and fill them into variables. So it's similar, you say target include directories, target link libraries, and you give these variables that CMake has declared for you. However, in CMake, a variable, it's just a string. So what really happens there is that you get hard-coded paths here to your PC. And now, if you want to install foo, this is where the fun starts, because the users of your library will not say, okay, we need to find protobuf, but they will see, oh, I have to find this C program files protobuf.lib, but I don't have that. That's a problem. So we had to learn this really the hard way, like a long time ago, using WX widgets, because they didn't provide targets. CMake find package didn't provide targets. So our library, which built on WX widgets, it was really a nightmare to export that then in the end. Okay. And last, for this chapter, I want to touch upon a pattern that you also often see in open source libraries, I would say, not being explicit when handling dependencies, but you should be. Okay, so let's take a look at the last example. We have a find package call there for JPEG. If we have found that package, we will build our subcomponent with JPEG support. So yeah, if it's found, we also add foo JPEG and link to the JPEG target. So also, yeah, why not do that? It's like, I don't have it on my PC, I don't need to build that part. The problem with this approach is the outcome is not deterministic. So when I build on my PC versus I build on a on a Jenkins CI machine, I get non-deterministic outcome, and this is not what I want. Basically, especially when I want to package this thing. I always want to have the same outcome, no matter what is installed. So what I recommend, on the contrary, is to create an option for your library. I want to build with JPEG support, yes, no. And then you can required find the package. If it's not located on your PC, you can still set this option to off, but at least you get deterministic builds. Okay. So we got 4 points down of our 5 points, how to write clean CMake code. So what's the last point? Well, keep your CMake lists clean. And I think it's a really important point. So what you often see is also for open source project, you see long and cluttered CMake list txt files. Our library, also not the best example in that regard. Our main CMake file is 604 lines of code. But my personal nemesis, HDF5 library, it's 1,230 lines of code, main CMake file. And we've had, HDF5 and I, we've had a lot of fun together, trying to build, trying to cross-compile, and when we integrate it in our build, we have to have like 70 lines of code just like unsetting and setting certain variables, which they're just overwriting for everything to actually not mess up our own install. So I think that there's some misconceptions of what should be done in a CMake file, because these files often used to like just configure everything. But new CMake versions, on the other hand, they provide powerful enhancements on what you can do to keep your files clean. So, well, first I recommend to treat your CMake code like production code. So that means you can use tools that you would use for regular programming. So try, don't you repeat yourself. Write functions, for example. Also write meaningful names for your CMake variable, because other people might have to read your code, actually, and understand what's going on there. The second one is you should distinguish build settings from usage requirements of your library. And really try and look at the code from a usage perspective. And for that, I want to show you first this simple example, and to understand how target property initialization works in CMake. So on the left hand, these are things that you also often see. So on the left side, you say, I'll set the CMake standard to 17. I add some compile options, and I don't want to target compile options because, yeah, I want this to be everywhere in my build. I want everything just to build with W all and W extra. And then I'll add the library. So when you do that, what actually happens is they influence the default properties. So we looked at the properties before. We're going to look at some other properties now. So these settings of variables and these commands, they influence how CMake initializes these target properties. So by setting CMake CXX standard to 17, when you add the library foo, it will have that target property. And the same with the compile options. So let's take a look at this code. And what's the difference really between this code? And I highlight for you the difference between the code. It's just like we have the library, it's the same as before, but we're using C++17 now. And we want it to be able to build successfully. So we could either say on the left side, we set the CMake CXX standard to 17. On the right side, we can say, we target compile the feature, foo public standard CXX17. And this is really conceptually a difference, because on the left side, we're making a setting. We say, I want to build now with that compiler. But on the right side, we're creating a usage requirement. We're saying, in order for my code to compile, I need at least C++17 standard activated. And then it shows really what happens internally when you try to install this. Because on the left side, you know nothing about C++17 standard, and users of your library have to activate that standard manually. However, on the right side, a target property will be set, and this will be the interface compile features. So anyone who's now using your library will automatically have that standard activated for their build. So the next slide. What do you think, which code is better of these two? I mean, okay, I highlight this. I think, who thinks the left one is better? Who thinks the right one is better? Okay, we all agree. So think about it this way. In the right side, this include of the header file iostream is a usage requirement for your code. The code needs this header, and the header will provide the definition of the standard cout. However, the compiler will provide this file and set from outside the include path accordingly. So for C++, this seems really, really obvious. However, in CMake, this is just not what we do. So, really important point. We want to inject build settings from the outside. So, I mean, yeah, we need settings. The compiler is a setting, the flags are settings, but injecting these settings from the outside are the builder, the user's choice of the library, but not the author's choice of the library. So let's see how that applies to CMake and what we can do in CMake now. So as I said before, you would often see this code, yeah. If we're on Unix, we just add those compile options to our code. But now, anyone has to build with these options. The user has to use it. Even worse, maybe you put a W error on there too. Then there's a user who's using a different compiler, a newer version of the compiler, and your library break builds. So what you can do is separate these. So keep your CMake files clean. Remove everything that you want to build, like settings that you want to make from your build, from your main CMake file, and inject them from the outside. So you could inject them on the command line. Not so nice when invoking CMake. But since CMake 3.19, we have a different mechanism for that. And these are preset files. Presets, they're awesome. They allow you to really separate build logic from the build configuration. And I think you can probably do a whole talk just about these new presets. And they can influence the whole build process. Right here we see configure. We see configure presets, but you can also have build presets, test presets, package presets, workflow presets. So with these files, you can then go to the CI and invoke your whole build just by running one command. You can compose and reuse these presets. You can also have user presets that are then applied only on your machine. But anyway, so now if you want to build this, you would go and say CMake dot and then -- preset Unix, and you get your flags. But you don't force them upon the user of your library. Okay. And the last point really which I want to make is we saw this now with the W all. You should think really carefully of what is really a usage requirement of your library. So I think a usage requirement of your library should be all that is necessary to build and consume your library correctly. But it definitely should not be setting the MSVC runtime to static library, which we had and which was really painful to find. So, yeah, communicate these requirements from the build to the user, but leave the choice of everything which is not mandatory up to the user. So, you made it. So, you made it through the 5 ultimate steps to be able to write clean CMake code. You know you should use CMake. You know you should understand how CMake works internally, or hopefully you know now how CMake works internally. You can package your libraries with CMake. You can handle the C++ dependencies in the right way, and you're hopefully able to keep your CMake files clean. And I think that if you're following these guidelines, adaptation of your open source library will be really good, and it will be a really good user experience for the user. So thank you for your attention.
Thanks for the talk. I have a question regarding if you have, let's say, a multi-layer of dependencies of libraries, and you need different versions of those libraries because of API breaks or whatever. How would you recommend to handle those cases?
It's really difficult. I think you should try and resolve the build so that is really not required, because it can lead at runtime to unexpected problems. For example, if you have, we just ran into this recently, you could get multiple defined symbols then in your later executable of the same library and actually jump into the wrong functions.
Yeah.
So I recommend, and Conan helps with that, to really create a build in which you have a build tree which does not need you to have different versions of different libraries. And usually there's a way that you should be able to resolve it.
Okay, thanks.
I have more of a comment than a question regarding vendoring and fetch content, for example. You recommended against using fetch content, but I know that there are several libraries already out there. I'm also a little bit guilty of writing such code that uses fetch content and gets the dependencies there. But I'm not sure from what version of CMake, CMake 28 or something, fetch content and find package are now tightly coupled. And with one little variable, you can instruct fetch content to, when it gets called, the fetch content declare, that it first tries a find package call for this library. And only if that fails, it then does the traditional fetch content way, and even the other way around. So if you have a find package, you can first try the fetch content, I think it was something like that, and then the other way around. So they're tightly coupled, but the first thing is more important. I think that fetch content can be instructed to use find package. That's at least how I was able to get a dependency of my dependency in the correct version, which I provided, and which could be found by find package without having the need to edit these fetch content lines in the third-party library that I was using directly.
Okay, so if it now works like this, maybe it's not such a strong point anymore. You're right.
Yeah, and the other thing I just wanted to mention, the dependency provider feature, which came with CMake 3.24. That's really, really powerful. I still need to look into it more in detail because I find it quite interesting. But I know that at least Conan 2, so the updated new version of Conan, is highly depending on this feature to hook itself into, and it works quite smoothly. So
Yeah,
that's a really powerful
I think it's a
thing.
really good and powerful feature.
So in general, I would say, as you already recommended, if you have the chance, use something like Conan, or I'm not sure how VC Package handles this stuff, but probably similar. Use a package manager, and they are tightly integrated now and work smoothly with CMake. At least that's my impression. Just my 2 comments.
What is the right thing to do when I'm building a static library that depends on other static libraries? And I kind of don't want to bother my user with having to list all those other libraries in his final linking step, if you know what I mean.
Yes, so CMake will take care of that. So when you're using target link libraries with your library, and then you're exporting that, like I showed earlier, then your user only has to link your library, and the other linking of the other libraries will be done transitively automatically.
Yeah, so in terms of CMake, you only write target link libraries. But
Of your library. But internally, it will propagate everything to the compiler.
Yeah, and in the command line, there will be
They
all
will
the
all
libraries
show
listed.
up there, yes.
Yeah, thank you.
Hey, hi. It was a very nice talk with a lot of information. I have a question. So we are building an binary, basically, which depends on multiple libraries which we internally build. So does it make sense to export these libraries as well? Because we are the only consumer of those libraries. So should we export them?
So if you build everything together, if you have like a monorepo and build everything there, there's no need for you to export them really. But if you want to make them available to other users, then of course you should export them. So if you want to install them separately from your application, so others can use that, then you should export them.
Okay, yeah, thank you.
So I recently started to kind of abuse targets for common compiler settings, even if so add library, and I attach public compiler settings to those because I don't want to introduce the compiler settings as globals, but want many other targets to inherit from that. And as there's no real library attached to that, it's kind of feels like a code smell, and I'm not really sure.
So you're doing like an interface, you're doing an interface
library. Sometimes an object library, because I also want to embed an MS Build manifest into it.
Okay.
But mostly an interface library, and I'm not sure if it's over-engineering or if there's a better solution to propagate such dependencies to many other targets without having to set.
So you only want to propagate them to a subset of targets, because otherwise you could use the presets approach, I guess. And
I could, yeah. And
it kind of depends. Are you exporting those targets and making them available for other users? Because if you are, then do they need these flags? I guess the resources they probably do need, so then I think for that use case the approach would be okay.
Okay.
Just a short comment again regarding the presets. I like them, although when I try to use them, I really quickly found out, and I saw, because some issues exist for that there's a big combinatorial explosion happening. If you have too many settings, it's really exponential, the different combinations you get. And I think currently, at the current state, this is still not solved, so you have to write a lot, or generate, that's probably better, but a lot of preset files or entries. And I would like to get that fixed, and I think then presets are really simple to use and also to write. Otherwise, currently I would recommend you have to generate them. Otherwise, it's too much of a hassle. At least my experience.
Yeah, I kind of had pretty much the same question, but yeah, I don't know. It's good. Maybe it's possible to like use custom toolchain files for that, or maybe as well. I saw this like thing where you can inject CMake files before the first project call.
Yeah, you can
Stuff
use
like that.
CMake top level include. So then you can just put them into a regular CMake file. You would say like Linux settings.cmake, and then when you build, you can just say -d CMake top level include. Then it will include this file before everything else. And in the preset, maybe you just say, okay, the Unix build takes this CMake file as top level include.
Okay, so there's a few questions from our online audience. One of which is, you showed the install command but did not mention CPAC. Do you use CPAC in your company setup?
We kind of use it, but I'm not the hugest fan, to be honest. It's a bit difficult with the setup, and I cannot give such good recommendations for it.
Thank you. The session is over, I think. So the other online questions probably won't have the time to ask them, sorry.